Hi, in this video, we want to take a look at disease mapping in terms of spatial statistics. All right, so our goal here is that we're going to take areas on a map, such as neighborhoods, counties, states, countries, and we're going to take disease counts, population counts, and we want to statistically model what's going on so that we have deeper insight into what's going on with the epidemiology. All right, so here, we're going to be working through examples from applied spatial data analysis with R, Chapter 10, disease mapping. Here are the authors of the textbook. Here is the textbook's website, and you can download the textbook for free through UCF's library. All right, so we're interested in the spatial variation of the incidence of disease. So we want to detect areas where diseases are, where the disease of interest is particularly prevalent. And we also want to use this insight to help us detect like unknown risk factors. So if I have subject matter knowledge about each of the individual regions, and I see that the disease is more prevalent there, I might be able to infer potential risk factors that I didn't know about beforehand. All right, so when we're doing disease mapping, we're trying to get a spatial distribution of the risk of the disease in our study area. The risk may reflect mortality, that is the deaths from the disease, or the morbidity, that is the number of people who suffer from the disease over the time span and for the population that we're studying. All right, so if you think about this, we really need at a minimum two things to be able to approach this. We need the population at risk in each of the areas that we're interested in, and the number of cases in each area. Also, if we want to be doing visualizations, we'll need the spatial data of the polygons that define the regions. Now, after I have this data, typically what happens is that we have other like categorical or numeric variables, stored along with our data. And so for the strata, this could be sex, age, or other demographic variables. All right, so by having the different groups in our data sets, we can explore potential confounding factors, and we can try to address these things with our data, and we can try to improve our models when we have this included. So something that can be useful for this type of work is the Deprivation Index. And here's just one example of it. There are multiple variations of a deprivation index, but we take into account income, employment, education, health. These are like household levels, and then these are neighborhood levels of crime, barrier to housing and services, and living environments. I copy and pasted this from Wikipedia. There are lots of different indices that we could potentially compute, but this is the one that the textbook talks about. All right, so as we tackle this, one thing that we're going to do is that we're going to say that subscript I connects to the region of interest, the subregion that is. J connects to the stratum, so that could be male, female, Black, Hispanic, white, Asian, American Indian, and so on. So PIJ is the population of the stratum, so the particular demographic of interest in region I. O sub j is the count of cases. So O is the observed cases of the disease, and then the IJ indicates region and stratum. E is the expected number of cases. Of course, we have I and J for region, then stratum. Now, when I do an underscore, or subscript, if I do subscript plus sign, this means this is for the entire region that we are interested in. And so here, P sub plus is just the total population of our study area. O plus, it's not a blood type for this one. It's the total number of observed cases. All right, so once we have that, one thing that we would want to have is what is the overall incidence ratio across all stratums in all regions? Well, to get that, I'm just going to take the number of observed over the total population. All right, and so what we're going to do, we're going to say that the expected number of cases for a particular subgroup, subregion that we're interested in is going to be the overall incidence ratio times the population size that we're interested in. All right, and so this is, you know, this is going to be a relatively coarse number, but this is like the overall, you know, population mean estimate for what's going on. Now, internal standardization is what we're going to do is for the subgroup of interest, I'm going to sum over the other index and get this. So here, I'm saying J means that we're interested in a particular population subset. So like, let's say I'm interested in female or male, Black, white, Hispanic, so on. And then I sum over all the regions of the number of cases. And then I divide by the sum of the populations. Okay. Now, we could also do this for regions. We could do this for, you know, we do this for any demographic. We can compute this multiple ways. All right. So when you're reading the literature, the number of observed cases is frequently called the numerator, and the population is also called the denominator. All right, so let's go ahead and start working on the actual computations. So let's go ahead and get the shape data and extract the FIPS ID number. So each county is going to have an ID number, and we're going to be working with North Carolina SIDS data from the 70s and 80s. And so here is the shape file that I need. It's in the SP data package. I'm going to set up my projection. And now I'm reading in the shape polygon. And here I'm specifying what the ID number is, and I'm specifying what the projection is. Now here what I'm doing, I'm just extracting the IDs. So I'm taking each of the polygons, and I'm taking the ID off of each polygon. And I'm using sapply to do this quickly instead of having to do a for loop. And now I'm going to load the neighbor object. All right, so remember, whenever I'm doing a local computation, I'll need to set up which regions are neighbors of each other. And this is a critical step in the process of building my models. If I make a poor choice on who neighbors who, then I'm going to get crap in my model. And so when I decide which counties are neighbors of which counties and how I make these decisions, this can make or break my project. So be very mindful about this. One thing that is especially of concern is that if I have neighbors that are like too far apart from each other. So imagine if I have two counties where they have a common border, but their populations are on the opposite sides. Then practically speaking, they're not neighbors, even though they share a border. Another situation is if I have very small counties, then it's possible that with sparse population, I don't have enough data to small enough, the population size is so small that I'm not able to really get a stable, reliable estimate. And then I might want to consider expanding out what I call neighbors between counties. And I can pick and choose for each county who its neighbors are. It doesn't have to be a symmetric relationship. So we have that flexibility in R. All right, so now let's go ahead and look at some global statistical models. The chapter is called Statistical Models. Really, this should be global statistical models. All right, so what we want to do, we want to use the entire study region to model disease at the subregions. So the estimators are going to borrow information from the global area, from the entire study space, so that we get stable and reliable estimates. This is a good idea if I have, let's say, very sparse numbers at individual locations. I can borrow the information to get a more stable overall estimate. Now, the disadvantage of this is that this is a very coarse approach. And since it's coarse, I'm not tailoring things to the individual data that, or the individual counties that I see. So we have to make a choice. We need a balanced point of view. Here, this is definitely a good place to start. I would definitely do global models before I do local models in my analysis. So global estimators do not consider any of the spatial aspects of subregions. So it doesn't consider the locations, which regions are neighbors of each other, distance between counties. None of that is part of the equation. All right, so it is super common to use the Poisson distribution when I'm handling counts. So we're going to do that here. We're going to say that the relative risk times the expected value is our Poisson distribution mean, and we're going to say that theta sub I is our relative risk. Okay, so a relative risk of 1 means that the risk is equal to the overall average risk of the reference region. And so here, this is it's of interest to find where the relative risk is significantly bigger or different than 1. So if it's bigger than 1, it's saying that we have more disease risk. If it's less than 1, we have less. Now, something about this format is that implicitly we are assuming that there's no interaction between the risk and the population strata. So the relative risk only depends on region. We, at this point, are not considering subpopulations at all. All right, so a standard calculation in epidemiology is to take the standardized mortality ratio. And so this is just our number of observed cases divided by the expected number of cases. All right, so for this, for the rest of the video, we're going to be taking a look at the 1974 data. And so I'm going to say that the observed is the number of cases for in the data set for 1974. We're working with SIDS data. Very sad. So let's compute the overall rate, then use that to compute the expected counts by county. All right, so to get the expected rate, what I'm going to do is I'm going to take the sum of the observed cases. So I'm taking the observed cases in each county, and I'm taking the population in each county, add it all up, I take the ratio, and that's my overall rate. Now, what I'm going to do to get the expected value is I multiply the overall rate for all of North Carolina times the population in each county. And so this is my estimate of the expected value of number of SIDS cases per county. Now here, I just go ahead and put this onto the data set. So I'm taking my SMR and I slap it onto the spatial polygon data frame. All right, so let's go ahead and take a look at what's going on. Okay, so what I'm going to do is I'm going to take the log of SMR. Now I'm going to restrict this only to cases where it's positive. So I don't have any zeros floating around because logarithms will give me problems. If I have zeros, I'm going to take the number of steps to be 7. Work out the difference of the range of the log that I just computed, And then I'm going to break up the color palette in this method. So notice I'm using the exponential. That's because of the logarithm. And we're just, all of this is just setting up the color palette for the plot. This is working out the cuts. And here I'm actually doing the plot. So let's take a look. All right, and here we can see that we have got greater SMR in the red region, lesser in the blue. If I see something close to 1, like here, then that's a sign that I don't have more or less than expected. In the light blue, we see that it's, it's probably lower than 1, lower than the expected. The observed are less than the expected, and in the dark red, the darker reds, those are more concerning regions. All right, so we have a probability distribution. Since I have a probability distribution, I can go ahead and compute a confidence interval for each of the standardized mortality ratios for each of the counties. And so to do that, I'm just going to use EpiTools, Poisson extract. I give it the observed and the expected. And this will end up giving me a data frame. I'll go ahead and tack on the names of the counties. Here I'm putting on a label just to make things a little bit easier to look at, to read, figure out what's going on. And you'll notice that confidence interval includes 1. So I'm specifying if we have less than 1, greater than 1, in terms of confidence interval, or the confidence interval includes 1. And I'm going to color the plot to make that easier to find. And here I'm sorting my data. I didn't have to do this. I definitely went overboard on how much of sorting I needed, but this is just setting it up so that after I do my plot, things will be easier to read. So now let's go ahead and visualize the confidence interval. I'm choosing to do this in ggplot. And how I approach this was I broke up each of the counties into 3 groups. And you can see that here I put all the ones that have statistically less than 1 in terms of the confidence interval. These counties have their entire confidence interval is lower than 1. These counties here, their entire confidence interval are greater than 1. And then all the ones that are in black are the counties that the confidence interval includes 1. And so we can just kind of see what's going on. And the points give us the SMR estimate, while the lines show us visually the confidence intervals and also show us the widths of what's going on. So if I see it's wide, I have less confidence in what's going on. I have a less precise estimate. Now here is how the author of the textbook did it. I didn't like this as much because it's hard to tell which county is which. It's hard to read what's going on. So I went ahead and sorted it and broke it up into subgroups. All right, so now let's talk about the Poisson gamma model. All right, so the Poisson distribution requires that the population mean is equal to the population variance. If the data's variance is greater than the mean, the data, we call this over dispersed. All right, so if we're confronted with the situation, we know immediately that this is not the best fitting model I possibly could get. One option we have to get around this is we use the negative binomial distribution instead of Poisson. So what we're going to do, we're going to tackle this by running things with empirical Bayes smoothing. All right, so what we're going to do, we're going to say that our relative risk is a gamma random variable, And then we're going to say that our Poisson random variable is the relative risk times expected number of cases. And so our observed cases is a Poisson random variable with this relative risk times expected as our expected value. So this is, in fact, a conjugate prior Bayesian model. I like this a lot. Conjugate priors are a heck of a lot simpler than Monte Carlo Markov chains. Easier to interpret, faster to work out. If this is a good option, I would greatly prefer a conjugate prior over a computationally intense prior. Here is our expected value of relative risk. Here's the variance of relative risk. Notice which version of gamma is coming into play. There's two ways to write the gamma distribution. In the exponent of E, we either have the parameter be in the denominator or numerator. Here, it's in the numerator. So in this model, the observed counts are conditionally Poisson distributed with a dependence on the relative risk. If I go through and I compute the unconditional distribution of the observed counts, we're going to get negative binomial with parameters nu, so the nu up here in the gamma, and then alpha divided by expected plus alpha as the probability of success. Now, how do we work that out? Well, it's just a straightforward, simple computation that I'm interested in the distribution of the counts. So what I'm going to do, I'm going to integrate out things that are not, I'm going to integrate out that theta. And so I'm going to take the integral from 0 to infinity. Theta is a gamma random variable, so that is its support. So here I have the Poisson distribution. Here I have the prior distribution. And now this next step is I'm just rearranging terms just like you do in this is really just like a college algebra manipulation, but you'd be doing this in, late Calc 1, Calc 2, something like that. All right, so I get this just rearranged, cleaned it up, made, put similar things together. You'll notice that all of my thetas are here and nothing here has a theta. So I'm ready to do this integration. Now I look at that and I go, whoa, that's variable of integration to a power and then E to a coefficient times variable of integration. I know that that is the gamma function. All right, so what I can do is I just go ahead and connect this to the gamma distribution. I realize that this is the gamma distribution without the rescaling coefficient. The integral with the integral of the distribution integrates to 1. If I multiply the distribution by the reciprocal of the rescaling constant, I know that the integral has to be equal to the rescaling constant, and that's how we get this stuff worked out right there. Boom, easy peasy, lemon squeezy. Now, what I'm going to do on this step after I've got it through the integration, I'm done with my calculus. I'm just going to rearrange the terms. And there's supposed to be a K here. Is that right? Yeah, there's an error on this. It's close, but not quite. The K plus V should be an exponent. This should be in the exponent position. You can see that in my LaTeX code. I tried to put in an exponent, but I messed up. I'll fix that for the class. All right, so now what I'm going to do, I'm going to take K of these, match it up with E sub I. I'm going to take nu of these, match up with alpha, and you'll notice that's where I get this and I get that. Now everything left, I've got a gamma, I've got a gamma, and I've got a factorial, which itself is a factor gamma. Remember that there is a relationship between the gamma distribution or gamma function, there's a relationship between the gamma function and factorials. So I look at this and I realize that this is in fact a binomial coefficient. Boom, I've got it. Easy peasy, lemon squeezy. And now I look at this and I go, huh, that looks familiar. This is new successes with this probability of success, where this is the random variable, k is the random variable for the negative binomial distribution. Boom, we're saying that the counts are unconditionally negative binomially distributed. All right, now the conditional distribution of relative risk, given the observed counts, is also a gamma distribution. All right, so what we want to do is I want to figure out what's the distribution of the relative risk. All right, well, here's the equation I've already got set up. Now, here I've got everything here. What I want to do, I want to rewrite this in terms of just the thetas, just like I did before. We can see, so if we're in terms of theta, the expected value, the k, the alpha, the nu are all constants in terms of theta. So I've got this theta part here, and I look at that, and I realize that that is the kernel of a gamma distribution. Therefore, the conditional distribution of the relative risk given the observed cases is gamma. Boom, we got this. Now, here I'm actually inconsistent with my O's and my observed cases as O's sometimes and they're K's. I don't like using O because it looks like a 0. All right, so if I take the posterior expected value of the relative risk, we see that's actually a weighted average between the SMR and the prior mean relative risk. The larger expected number of cases will place more weight on the data, which is computed, which is how we get the standardized mortality rate. So if I have fewer expected number of cases, that's going to put more emphasis on the prior, not on the actual observed data. All right, so here, if I do the computation, the expected value of theta given E and O, just taking this part here, I know the distribution. So here I get the expected value of the relative risk. And now I'm just doing some college algebra to rewrite it. It's a little bit tricky, kind of surprising, but I see that after I'm all done, this is the SMR, and this is the prior mean, and then these two can be interpreted as weights. Boom, we got it. All right, so when E is small, such as when we have small populations, small variations in O, in the number of cases, can have a large impact on our standardized mortality ratio. Now, the estimates of relative risk prior use data from all the regions. So it follows that these estimates are going to be less sensitive to variations in data. All right, so now let's take a look at empirical based smoothing. So I'm going to be using R code to do this now. So here, this is our relative risk estimate. Here's our estimated, the expected value, estimated expected value, and here's our estimated variance. Here's how we compute it. And here, we're going to use the decluster package, empirical based smoothing. I give it the observed, I give it the expected. It's going to compute the smooth relative risk for us. Here's nu, and here is alpha. And we can take a look. Here's our nu, here is our alpha. So now let's go ahead and calculate p-values doing this. So what I'm going to do, I'm going to take the cumulative distribution of the Poisson distribution. here is our quantiles of the observed. Our expected value is the expected value. And I'm going for a p-value. So I'm going to say lower tail equals false. And then what we're going to do is we're going to compute the same thing for negative binomial. I give the observed, I give the size, and I give the probability of success. And these are being computed using the calculate the maximum likelihood estimate from the dCluster package. So I'm converting my spatial polygon data frame to a regular data frame, and I'm saying go with the negative binomial. Now, something that's important is that observed and expected need to be labeled columns in the data frame, and it'll do everything for us. Now let's go ahead and visualize the p-values. The author of the textbook likes to call it a probability map instead of p-values. It's actually contradictory to the professors that trained me, but whatever. All right, so here we can definitely see that, that we have some more extreme p-values with the Poisson distribution, and the negative binomials has, definitely smaller values in the same regions, but not as extreme. All right, now let's take a look at a log normal model. All right, so what we're going to do, we're going to assume that there is a beta that's equal to the log of relative risk, and these betas are going to be multivariate normal distribution. So our estimate of relative risk is going to be the exponential of the multivariate normal distribution object. So beta as a vector is multivariate normal with constant mean and constant diagonal for a variance matrix. All right, so here you'll notice that I have zero covariance between all values. That's an important assumption. And the phi and sigma squared are estimated using expectation maximization. All right, so our estimate of log of theta is going to be number of counts plus 1/2 divided by expected value logarithm. The reason why we have this 1/2 here is because if I had zeros, we would have potentially we could have zeros, and zeros would give me problems inside that logarithm. So just to make sure we don't have any issues, we say 1/2 just so it computes. And so here is our beta hat like this. Now, in this process, this is going to be iteratively computed. There's going to be a back and forth until we have convergence. It's going to compute one of the estimated values, use that to improve the current estimated value of another, and then go back and forth until we get convergence, so we get better values. And so to get this, once again, we're going to use dCluster. We use log normal, empirical Bayes. We give the observed and we give the expected, and it works it out for us. And then we can take the exponential of our smooth relative risk to get our estimate for each subregion. All right. Now, Marshall's global empirical Bayes estimator, what this is going to do, this is going to assume that the relative risk across all regions have a common mean and variance, but does not specify the distribution. Okay, so this will be a little bit more flexible. If we don't think that the assumptions that we've had previously of Gaussian, Poisson, negative binomial, and normal don't apply to the situation, maybe we believe that the probability distribution aspect is so exotic that we don't want to use those modeling assumptions, we can go with this particular global method. It does not use any particular distribution. It just specifies expected value and variance is constant across the regions. All right, so if we use a method of moments in this technique, we're going to see that we're going to get a weighted average between the estimated mu and our standardized mortality ratio. The C is given here, kind of an ugly formula. And the mu, definitely makes sense. The total number of observed divided by the total number of expected. And when we say S squared in these formulas, this is the estimated variance of SMR. A flaw in this is that we could actually get negative values if the estimated variance is less than this ratio. When this happens, we would just use the naive, simple global estimates. Now, the shrinkage estimator is highly dependent on the expected value of cases. If the expected value is large, typically with larger populations, then our standardized mortality ratio is more reliable, and the C will be close to 1. If the expected value is small, usually with smaller population, then our SMR is less reliable, so there's going to be more weight to that global estimate. Now, to go ahead and do this, we'll go ahead and use SPDEP. We're going to use empirical Bayes estimates. Now, something that's important to notice about this is that if you read the help documentation, this X is for the population, not the expected number of cases. And so this is, the author is going a little bit different than how it was originally written for. But the function is actually estimating, population is trying to estimate rate, not relative risk, and we're just retooling it here. So the empirical Bayes estimate smooths out extreme values. And so that we'll see, typically, we won't really have nearly as many extreme values as we would with other methods. And things will be kind of like smoothed out towards the middle. All right, so we can see that visually, when I look at the 4 different methods, the empirical Bayes techniques all give pretty much the same visual map. There's a little bit of difference. And we can see that there aren't nearly as many extreme values. When I look at the SMR, which only takes into account the cases and the expected values in that particular county, we can see we get more extreme values going on. Now, in the next section, spatially structured statistical models, this is different from what we've talked about so far in that previously everything was global. Now we're talking about local. In the global estimates, we use calculations that included all the data for all the regions. And now, in this section, we're talking about when I'm interested in a particular county, I only use neighbors of that county. I don't use the whole data set. An advantage of this is that the calculation result is more tailored and more specific to what's going on. A disadvantage of that is those calculations are less reliable, they're less stable because I'm using less data. We have to weigh this to make a choice. One thing I could do if I feel like I have too little data, I could always increase the size of the neighborhood for an individual region. And remember, as I go through this, I do not have to have symmetric neighbor relationships in R. So it's sensible to limit subregion neighbors to subregions that border each other or are within a given distance from each other. a lot of the local estimators are basically the same estimators as the global counterparts, but subregions are calculated using modified global regions, is really how mathematically it works out. I would always analyze the global structure first to make it easier to interpret. It's absolutely critical that we get location and neighbors right in these types of calculations. If I mess up my neighbor choices, I mess up my entire model. Garbage in, garbage out. It's especially sensitive to the choice of which regions neighbor which other regions. So let's go ahead and do a local empirical Bayes estimator. So we're going to compute the estimate shrunk down to a neighborhood mean of neighborhoods given by the neighborhood list. And so here, when I do empirical Bayes local, once again, I give the observed, I give the expected. Now the difference from previously is I have to specify the neighborhood. Now let's go ahead and visualize it. So here we have local and we have the global estimate, and we'll notice that when I'm looking at the global estimates, once again, the extreme values are kind of like pulled in towards the middle, and the local ones, we have more extreme values. I personally, for this one, I think the local is actually the better way to go. All right, so now let's go ahead and use box plots to kind of get a feel for what's going on. The goal of this visualization for me is to show you how much more variation we have between these different models. You'll notice that SMR, which only relies on the data for the individual county, has the greatest variance, the greatest spread, greatest dispersion. The local calculation has more than the others, and then the ones that use empirical Bayes are the ones that have the least variation. And here is the author's calculation. I like my ggplot better. Now, in the next video, I'll go over some Bayesian hierarchical models. And that's all I've got for you. Take care and goodbye.